Hello again, and until recently, that is until the last lecture, we discussed how to obtain energy bands. So, the discussion was basically to obtaining the energy dispersion relationship, the E k function. One of the things you can actually get from the energy versus k function is the Fermi energy. We can get the Fermi energy, which is the energy of the highest occupied state. Okay. So, I can say that we can get EF, which is a Fermi energy, and in metals there is a collection of points for which energy E of k is equal to EF and we call these points, of course, the kf are the points which form a surface. So, the idea is to know more about Fermi surface. So, we can calculate the Fermi surface from energy band calculations. The Fermi surface. The question is, can we measure it experimentally? The answer to this is yes, and we can. There are many techniques for measuring the Fermi surface, and I will just list them and then we will discuss two of them in detail. Techniques for measuring Fermi surface. So, one of them is anomalous skin effect. We will not discuss anomalous skin effect, but I will just have occasion to mention what it is actually, and then we can also do a magnetoresistance measurements to get the Fermi surface, change the direction of the magnetic field with respect to the crystal axis, and you can get magnetoresistance data. From that you can get Fermi surface. You can also get the Fermi surface from studies of ultrasound propagation under the influence when the system is under the influence of a magnetic field. Studies on ultrasound propagation in the metal under a magnetic field. We can also measure the Fermi surface by doing optical reflectivity studies. Optical reflectivity measurements can give you information about Fermi surface. And some of the techniques that I am going to discuss are the cyclotron resonance measurements, and then another thing, a technique called de Haas Van Alphen effect. So, the last two techniques we will discuss in some detail. Now, coming to cyclotron resonance, what we know is that what is the force on a moving charge in an electromagnetic field. So, if we are looking at a charged particle, say an electron, charge is minus e, is an electron moving with velocity v, experiences a force in a magnetic field H, which is given by F is equal to minus E by C moving with velocity v cross H. So, if the magnetic field is in the z direction, if the field direction is z, then we have F is equal to minus E by C I j k V x V y V z 0 0 H z is equal to minus E by C I times H z V y H z V y plus j times it is actually, must be careful with the sign. So, this is minus, so minus j times V x H z, or we have F x is equal to minus E by C V y H z, F y equal to E by C V x H z. From now on I will drop the subscript z on H, because we assume that just H means application of the field along the z direction. Now, F x is equal to d m v x by dt. Similarly, F y is equal to d m v y by dt. So, I can write down V x dot is equal to minus E h by m c V y, and V y dot is equal to E h by m c V x. Of course, c is the velocity of light. We can solve this. This is just an oscillatory solution is there, and we can write down that V x is equal to V naught cos omega c t, and V y is equal to V naught sin omega c t. So, we see that this satisfies the differential equations, and so what it means is that the electron does a cyclotron motion, that is goes round in spirals, cyclotron motion in the xy plane. That means, if you take the spiral and project it onto the xy plane, then you have a circular motion. It is a spiral because the velocity Vz need not necessarily be 0, and so the electron will be moving along the z axis. At the same time, there is no energy absorbed from the magnetic field. That is because the displacement is perpendicular to the direction of the force, and because of that we will not see any absorption of energy by the electron from the magnetic field. So, we can actually show this one in the following way. So, this is the h or the z axis, and the way electron goes around is okay. So, this is the spiral that we are going to have, and there is a very famous theorem which is one of the rather simple theorems, and it is called Bohr-Van Leeuwen theorem. And this says that the electrons in a magnetic field if you forget the spin, that is okay, in a magnetic field are behave as non-magnetic entities. This can also be known from the fact that if you have a magnetic field can be represented by a vector field, by a vector potential. And the kinetic energy, because we are considering free electrons, so they only have kinetic energy, and the kinetic energy of free electrons is given by P minus EA by C the whole squared divided by 2m. So, if you have this, then you see that the partition function z, which is integral over e to the kinetic energy by beta by kT, and kT is the temperature. So, this one is d cube px does not change. In a magnetic field, and hence there is no magnetic response. Therefore, no magnetic response from free electrons, from classical free electrons. Of course, this is not true once you go to quantum mechanical solutions. Let us do a quantum mechanical calculation of the same thing. The Hamiltonian is given by minus h cross squared by 2m. Just one second, I want to make sure that okay, 1 by 2m. Minus h cross squared by 2m P minus EA by C the whole squared. Now, we know that the magnetic field H is equal to del cross A. So, if we take A to be the following: 0 times I plus xh times j plus 0 times k. Okay. Then what we will get is a magnetic field along the z direction. So, you can just see that I, j, k, and del by del x, del by del y, del by del z, 0, xh, 0 will give me k times h. So, now let us see what we can do with the Schrodinger equation involving this vector potential. The Hamiltonian for this will be given by 1 by 2m px squared plus py minus EH by C times x the whole square plus Pz squared. Okay, so given this, we can actually write it in the following fashion, that is, this is just nothing but Pz squared by 2m plus Px squared. This can be quite easily simplified, and when you simplify it, what you will get is Px squared plus Py by plus 1/2 m omega c squared times Py by m omega c minus x the whole squared times this is a Hamiltonian. So, if I am looking at H psi equal to E psi and I want to solve this, then what I will do is I will take psi is equal to, because it is a Pz squared by 2m and there is no other quantity coming into picture there, I can write it as e to the I k z z plus multiplied by, not plus. So, I could use the wave function as e to the I k y times phi of x. So, if I were to use this as the Hamiltonian, then I will get the following equation for phi of x. I will get Px squared by 2m this is Px squared by 2m. Px squared by 2m plus 1/2 m omega c squared times p by m py by m omega c. So, that will become it will become ky squared, but you know it is okay. So, m omega c minus x the whole squared times phi of x is equal to E minus p z squared by 2m, which is the kinetic energy for motion along the z axis, times phi of x. Because I have taken e to the I k y, then py will give me h cross k y. So, I might as well put it as h cross k y. What we see from here is that this equation is an equation for a harmonic oscillator which is displaced. The displacement is by an amount h cross k y by m omega c. This is the amount of displacement, okay, and is displaced, and hence the solution is simple, and hence E minus Pz squared by 2m is equal to some L plus half h cross omega c. I think I forgot to define omega c. Omega c is what is called cyclotron frequency. It is just given by Eh by mc, and you see this appearing for the first time in the Lorentz equation for force. So, you see that this appears for the first time here, and this is omega c. Having done this, then next thing we want to do is find out what happens when you are actually doing this analysis in the K space. So, to do the analysis in the K space, we look at the following picture. That is, we have the free electron Fermi surface we can draw. The free electron Fermi surface will be a circle, and in this the magnetic field is in the z direction, let us call it H, and we have a cross section. One of the cross sections that we will take is this one, and this is in the perpendicular plane to the magnetic field. So, actually I will shade it so that you know that it is a perpendicular. So, that is perpendicular to H, and we have V is perpendicular to the circle, and force K dot is in that direction. So, this is the direction of V and this is the direction of K dot. So, having said this, what we have from our Lorentz equation is the following: dk by dt is equal to minus, actually it is the momentum, so let me put a h cross here, is equal to minus E by C V cross H, or I can also write it as minus E by C H times V perpendicular, because H times V perpendicular, that is a definition of V cross C, and V perpendicular itself is given by the gradient of the energy surface with respect to K. So, I can actually write it as delta K E 1 by H cross. So, this is the gradient, and we know that the gradient is always perpendicular to the surface. So, it is going to give me V perpendicular, and hence I can write down dk by dt is equal to minus EH by H cross squared C times grad KE. So, actually grad KE is the group velocity. So, we know that, so V perpendicular is actually the group velocity, and I have got it as a gradient of the energy. We can find out the period or the time taken by the electron to complete one revolution. So, that is what? That is T is equal to dt, and that is equal to H cross squared by C by EH times integral dk upon grad KE, and grad KE in our case is equal to delta K perpendicular divided by delta E. So, if I were to draw put this in, T is equal to H cross squared C by EH cross, or H cross squared C by EH into 1 upon delta E and integral dk delta K perpendicular. So, what does it actually give you? So, let me write it down. So now I have a circle. So supposing I have the center is here for the sphere. So this is k and this is k plus dk. So this distance is going to be delta k perpendicular, and that multiplied by the energy, the difference of the two, which is dk. So that should give you the area of the shell. Okay. So what it gives me is that it is the area of the shell. So I have T is equal to h cross squared c by EH ds by dE. Okay, it is S is the area of the circle around which the cyclotron resonance is taking place. So I can also write omega c is equal to 2 pi by T So I can write it as 2 pi by h cross squared c into EH into dE by ds, because omega c is 1 by 2 pi t. If we have this, we can define an effective mass. We call it the cyclotron effective mass, mc star, cyclotron effective mass, which is 1 by mc is equal to 2 pi by h cross squared dE by ds. So we have an expression in terms of the effective mass. So I can say that omega c is equal to EH by m star c. So you see that m star is 2 pi by h cross squared dE by ds. So if you measure the cyclotron frequency, we can get information about the Fermi surface via dE by ds or ds by dE, whatever way you want to look at it. Now let us see how one can do these cyclotron resonance experiments. First of all, if you have a spherical Fermi surface, then if the Fermi surface is spherical, omega c is the same for all cross sections perpendicular to h. Perpendicular to the applied field h. So there is no problem. There will be a coherence of the cyclotron frequencies, and because of which you will be able to see the observation of the, you can measure the frequency. But what happens is that in general the Fermi surface is not spherical. Fermi surface is not spherical. So when the Fermi surface is not spherical, then omega c is different on different planes. Perpendicular to h. So because of this, there is going to be a destructive interference. Okay. So this leads to destructive interference and you may not be able to see the signal, and cyclotron signal may not be may get washed out. It will get cancelled or washed out. But there is a saving grace. The saving grace is that if the Fermi surface has extremal cross sections, for example, let me look at a Fermi surface which has a shape like this. So, the extremal cross sections are the following. This one is an extremal cross section, and this is another extremal cross section. So, when you have these extremal cross sections, the phase of the oscillations near extremal cross sections vary slowly. And do not cancel. So, if you do a cyclotron resonance experiment, then you should be able to get from cyclotron resonance experiments, you should be able to get extremal orbits of the Fermi surface. Able to see extremal orbits, and by measuring the cyclotron resonance in different directions of the applied field with respect to the crystal axis, then we should be able to construct the Fermi surface. What I am going to do is, I will tell you what are the problems that one has in actually doing this experiment in metals in the next talk, and I will also talk a little bit about the de Haas-Van Alphen effect and how de Haas-Van Alphen effect can also give you information about the Fermi surface. So, we will meet again next time, and until then, bye.